I'm Nathan Sheely, and this is my final project for CSCI E-95 Compiler Design and Implementation and Optimizing C Compiler. For this project, I implemented a compiler for a significant part of the C89 programming language, basically everything except for structs, unions, and function pointers, and I'm going to start with a brief overview of the project itself and how we turn a text file, a C program basically, into something that runs on a machine. First, we perform a lexical analysis. I used Flex. It's an open source lexical analyzer generator, providing it a specifications of tokens in the language, basically a bunch of regular expressions to relate what sequence of characters are what kind of tokens used later in the language, in the compiler. So we pass those tokens onto a syntax analyzer. I use GNU Bison. It's an open source parser generator. I provided a specification of the grammar, which it uses in order to relate the tokens and sequence of tokens and see how they're associated in order to pull out information of how the program works a little bit more. It places these tokens into a data structure called an abstract syntax tree, which is essentially a tree of nodes where its children are the things that feed up to its operation. For instance, you have a function here, and one of the children will be the contents of the function, and then like you'll have addition, and its contents will be the thing to its left and right, so on in that manner. And as you can see at this point with the information we've got here, we can actually print back out the original program with some brackets specifying the association of the different nodes at this point. From there, we can traverse over the abstract syntax tree and generate a symbol table. Symbol table is just some data structures to track information for identifiers in the program, such as their type and scope. So for instance, here we have our global scope, and inside of that we've defined functions main and fib. And we can look, we got the global fib function here, and it's got a variable in. And we can see in the program, like, hey, we got in, it's in global fib. All that information is there now. So with all this, we can now perform type checking, a semantic analysis over the program, and see if what we're trying to compile makes any sense in the language we're using. So we're traversing over the abstract syntax tree again, and when we see certain things, we find that information in the symbol table and see if it makes sense. Like here we've got an integer and a character array, and we're performing an XOR operation, which is not valid in the language, so we throw an error and we stop the compiling at that point. Additionally, we insert some implicit casts, so like if we're going between shorts and ints, those are valid operations, but the compiler needs to actually perform some casts in order to compare those different length data types. From there, we validate our program, and we're going to start generating some intermediate code. Essentially, this is like assembly, but it's machine agnostic. All the instructions can relate to different assembly instructions, but we have an infinite number of registers at this point, which is useful in a couple ways. So we can expand our compiler to compile to different machines now instead of just MIPS like we're doing here, but we can also perform operations on this IR, which would then be valid for whatever we're translating this code to. So the next step is to perform optimization, where we just take that IR and produce a new IR that is in some way more efficient. Either it's smaller, fewer operations, faster, that sort of thing. And we'll be detailing these specific optimizations that I've implemented later during the demos. And finally, the IR is translated into MIPS code. Most of the IR translates roughly one-to-one or one to a couple MIPS instructions. And the very difficult challenge at this point is keeping track of memory, where we're storing things in the stack, to push down, place stack frame when we call functions, and to track registers, see what information you're currently holding where in order to make sure your program actually works on your target machine, which doesn't have infinite registers. It has a finite number, and we have to deal with that here. Finally, I want to take a moment to discuss the debugging for this very large program. Ignoring anything generated from Flex or Bison, this is still over 10,000 lines of code. Tools like Valgrind and GDB were extremely helpful in finding errors that were going wrong, like if I was seg faulting or something of that sort. Additionally, I inserted a whole system of error statements that I could turn it on, off and on with these defines. So like if I was debugging my MIPS and be like, oh, maybe there's something actually going wrong in node or symbol or something like that, I can uncomment out these defines and I'll start getting tons of print statements for what's passing through there and seeing if what's happening is correct or not. So for my first demo, we're going to start pretty simple. This is the program we've been looking at all along. It's a simple Fibonacci number computation. In case you don't know, Fibonacci numbers are just a sequence defined by the sum of the previous two numbers in the sequence. So fib of n is fib of n minus 1 plus fib of n minus 2, where the fib of 0 is 0 and the first one is 1. Now this was a specific test that I think has been fixed and broken more times than I can count between the casting and this ternary operation. But this is a very ineffective way to compute Fibonacci numbers. As you can see, every time this is called, it calls itself 2 more times. This is an exponential time algorithm. Even with the optimizer, it doesn't stand much of a chance. Like, the optimizer can do some amazing things to help you out, but it's not going to fix really bad code like this. So we can do a little bit better. We can re-implement the Fibonacci function where it only calls itself once. So instead of exponential time, it's linear time. And as you can see, it took, what, 7.5 seconds to compute Fib 11 here. Before any optimization, we're down to 10 times faster, more than 10 times faster for Fib 11. And you know what? We can do, the compiler can actually really help us out now. We can do something called tail recursion elimination. So this return statement calling to itself has no further operations. So back here, we computed the Fibonacci number, but then we had to add it after we computed it. Here, we compute it and we're done. We go on to the next one. Every single time we call it, we push down the stack, we get a result, and all those are just getting called right back up once we're done computing. We can eliminate the recursion altogether. So here, we're inserting this label here, inserting go_to, and all of our parameters are just being stashed into the appropriate variables for the function call, and it just loops around. So branching might be expensive, but calling a function is a lot more expensive. And you can see that here, we can calculate fib 46 1,000 times. It'll take 2.5 seconds unoptimized, but we can get it down to basically a second after we've done optimizations. That's 2.5 times faster, which is pretty freaking good. So this is a fully functional compiler, so we can do a lot more than just calculating Fibonacci numbers. So pushing what all we can do, here's Conway's Game of Life. It is a 0-player game created by John Conway. It's a cellular automaton played on an infinite grid of cells. Each cell has 8 neighbors, and they have one of 2 states. They're either alive or dead. And the game is played by the following simple rules. If you have a live cell with fewer than 2 neighbors, it dies. If you have a live cell with 2 or 3 neighbors, it keeps on living. If you have a live cell with more than 3 neighbors, it dies. But interestingly, if you have a dead cell that has exactly 3 neighbors, it becomes a live cell. Now this was largely popularized in 1970 by Martin Gardner, and here's some key things he wrote. Basically just did them by hand. On paper, kind of like a math problem, saying like, here's this initial condition, it goes on, dies, and you notice, hey, these have become stable. When you get a block, it just stays blocked forever. If you get 3 in a row, it becomes this blinking thing that'll rotate back and forth. Now, with computers, we can do some more sophisticated things. Let me launch the program real quick. So, this is Conway's Game of Life. Specifically, this configuration is called Gosper's glider gun. So we've seen configurations that are periodic with that blinker, but there are also some configurations that will move. So these gliders, this is a glider, and it'll essentially move across the grid forever in a real Conway's Game of Life. In a computer, we have finite space. Instead of an infinite grid, we have walls, and it'll eventually reach the wall. Now, What's special about Gossamer's glider gun is that it's a configuration that repeats but also grows. It'll just keep going forever and create more and more gliders, which is pretty cool and instrumental in proving things like that Conway's Game of Life is Turing complete. You can use this to create create blocks that'll destroy gliders or let them continue and create NOT gates and AND gates and OR gates and build a whole computer out of just Conway's Game of Life. Oh, and this specific configuration was discovered by Bill Gosper in 1970. There are some other configurations I would like to show you, but for the sake of time, this is all we're going to be doing. So my thought here was Conway's Game of Life is using these two-dimensional arrays, and there's all this optimization you can do on it. So we start unoptimized. We got 10 instructions here. We can do constant folding. We see like, hey, we're multiplying 200 by 5. That's always 1,000. We can just turn that into one instruction here. And then we can see, hey, we're just adding the address of the array here to 1,000 to find the new position. It's always going to be like that. And we can just do add immediate instead of pulling out the variable and doing it. And then we see, hey, we're not using this constant anymore. We can do dead code elimination, remove that code altogether. But now we got an immediate that returns into an unsigned immediate or an add immediate. And we can fold those together because addition is associative. So you have this essentially a variable of the address of the array, and we're plus 1,000 plus 4, so it's plus 1,004. So we've turned 10 lines into 4 lines. And I was thinking, you know what, this is going to optimize pretty well. And for the sake of size, it did. It went from 896 lines to 614, so it's 70% the size. But if you look at the time, we gain 5 seconds, which isn't super fantastic, but we can see what went wrong here. So here's all these assignments. I'm like, hey, I'm gonna get all these gains out of this, but this only runs once. This is the initial setup. Almost all of the time this is being run for is here. It's these loops. We're printing off the grid. We're computing the next state of the game. And there's not a whole lot here that all those things I described are optimizing out. There's some, you know what, there's some flow control going on here. There's some go-tos and stuff being removed. But something that would have been a lot more effective would be like loop unrolling. If we could loop unroll this all the way to where it's just like constants, then all the other stuff would have done, and this probably would have just been fantastic. But you know what, live and learn. It was still a decent project. And I'll take a moment for a relevant XKCD. John Conway died in 2020, and Randall Monroe of XKCD made this configuration as a memorial to him. So we've seen we can do simple arithmetic, we can do something more complicated with Conway's Game of Life, a whole simulation. But you know what, when I use a computer, I want to interact with it. I want this back and forth thing going on. So what kind of interactive program can we make with this C programming compiler that I've made? We can do tic-tac-toe with its own AI. In case you didn't know, tic-tac-toe is a 3x3 grid where the game is played by 2 players alternating places X's and O's, and if you get 3 in a row, you win. Or if you fill the grid and there's no 3 in a row, it's a tie. So let's play against the computer. The grid is specified by the numbers of what the positions are, so I can be like, I want to be at position 1. And I'll play here, and then the computer will go to position 5 in the center because that's a good move. I'll put in 2, and it sees, hey, I'm about to win, and it's going to block me. 7, it's trying to strategically place for a new win. 6, place there. It's a tie. Let's try again. Let's see if I do a more strategic place at the center starting. And maybe let's try and break the game. Let's put in a bad number. Oh, can't do that. If I choose 1, can't do that either. So it's rejecting input that's not valid. And then I can put, let's actually play the game. Let's try and see if I can win here. And oh, I missed that 9 in the computer one. So the computer is actually really good. I have not beaten it yet, and I don't think it's possible to beat it. So for the sake of saying like, hey, can player 1 win at all? We're going to just play like it was 2-player and see, hey, I got 3 in a row and player 1 can win. So how well did tic-tac-toe actually optimize? Reasonably well. So it's difficult to actually perform analysis on this because of the input. So I just ran a couple times and saw this was typical. This is about 34 milliseconds unoptimized. If I do optimization without dead function elimination, about 30 milliseconds, and then I get down to 28 if I remove all that dead code. Dead function elimination is essentially, I was trying to make a different version of the AI using the minimax algorithm. I didn't quite get it working, but I left the code there. But it's now uncalled code, and I can just remove it. It's gone. I don't need to generate MIPS for code that's never going to run. And I got the size down to basically a third after all of that. Any questions?